Great, thanks for the introduction, Mattis. Thanks for inviting me along as well, Amos Melbourne Committee. Today I changed the talk title ever so slightly to be more general. So we're going to be discussing whether the use of weather radar in a larger context around Australia and going beyond just the traditional applications for rainfall. I'm a postdoc at Monash University, and I'm also often around the Bureau, which is why I often get referenced as a Bureau employee as well. But you often see my work associated with CLEX, which is a COE group for climate extremes. So I'll be talking about a couple of topics today. I'll be giving a very short primer on weather radars and retrievals, because we often find that public knowledge in this area needs some improvement, particularly about the new technology which is coming into place. Second, looking at climatology applications. Then moving on to looking at severe weather projects I've been involved in across Australia that have used radar. And then finally, a new cross-platform project called HAILTRACK. So starting off with the primer, looking at weather radars and retrievals. So our conventional radars, which the Bureau uses across the country, rely on a fairly simple principle. They transmit a pulse of radiation and then spend 99.9% of the time listening. So that pulse is on the order of 1 million watts, and it listens for scattered radiation, or whatever's out there in the pulse's path, on the order of 10 to the minus 15 watts. So that's our basic principle. One really important fact that people often look over when looking at radar data is the Earth curves away from the beam with range. So when you're looking further away from a radar, you have to remember that you're actually looking at a higher elevation as well, which limits what you can infer at the surface. And finally, radars, the radar beam scatters off everything, not just precipitation. So bugs, birds, bats, ships, planes, especially military aircraft releasing anti-air missile chaff, turbulence, and of course ground when the radar beam intersects the ground. This creates for a very complex and messy picture sometimes that we put a lot of effort into cleaning up. So the intensity of these returns of scatter, we call that reflectivity. And also a common product which is out there now is the frequency shift in these returns, and this is used to derive Doppler wind, which is a radial component of the wind. So in terms of what these conventional radars are collecting, we often see a 2D image on the web. They're actually collecting a full 3D volume of information. We call this data set a volume, and it's composed of many conical tilts in which the radar scans, typically 14 tilts in Australia. So a single volume is collected every 6 to 10 minutes, and it contains between 1 and 6 million data points where the precipitation is present. So these are collected across Australia on a network of 62 weather radars currently, and this is our largest remote sensing asset in Australia. Something that's slipped a little out of the news lately, it wasn't really picked up very much by media, but we've recently, at the Bureau, awarded a long-term framework contract for upgrading the entire weather radar network over the next 10 years. This is going to be picked up by a German company, and this will deliver a new type of technology. This technology is standard in many international countries now, such as the US, and across much of Western Europe. And I'll talk about this technology next, which is dual-pole radars. So dual-pole radars, the fundamental difference is they use 2 beams of radiation simultaneously, not just one. So these 2 beams, as we can see in the image there, they're actually perpendicularly aligned. So you have a horizontal beam and a vertically aligned beam. So the purpose for doing this is the horizontal beam is useful for picking up the returns from flat objects that are flat in the horizontal plane. And this in particular is falling water droplets. So water as it falls will flatten out into a disk, and it's picked up mostly across this horizontal plane. In the vertical plane, you have higher up in the atmosphere, ice crystals are often aligned in the vertical plane. So this beam is ideal for detecting the magnitude of scatter of these precipitation targets. So not only can you distinguish between ice crystals and water droplets, you can identify more spherical shapes such as hail. So using the two beams simultaneously, if they have roughly equal returns, you have a pretty good understanding that you're detecting hail. And this is a huge step forward from the conventional radar network, where heavy rain is almost impossible to identify from large hail. The other advantages of dual pole is it tells us about the coherence of shapes within the measured volume, so whether we've got lots of mixed particles or whether they're more uniform, and also how much phase changes occur, which gives us a really accurate idea of how much water is in the microwave beam's path. So having all this information about what is precipitation, it's really good for removing what isn't precipitation. So dual pole cleans out all of that clutter which we previously had due to bugs, birds, ground, and various other sources. And not only that, it opens the door to new products and improving our existing products, especially for hail and water-related retrievals. Moving on to retrievals now. So conventional radar is typically used first and foremost for rain rate. So there are a number of ways of doing this. Usually it's gauge calibrated at the surface and of increasing complexity depending on how accurate you want your rain rate. But the important thing to remember here is radar is not measuring rain at the surface. Typically it's hundreds of meters above the surface. So there's always going to be some correction needed to bring that measurement down. Secondly, conventional radars give us an indication of hail size on a 2D map, which is taken from higher up in the cloud where we know that the droplets have to be frozen. And we put this on the surface and assume that the hail is falling down onto those locations. Of course, you can get other retrievals such as the cloud top height, which is used a lot in climate statistics. And you can also apply objective analysis and pull out properties such as the individual mass of clouds, how much volume, area they have, how fast they're propagating, and their evolution over time. Adding in Doppler wind data, you can start to identify features which are dynamically based, such as supercells. Supercells have a very strong rotating updraft, which Doppler wind data sets can pick up. Not only that, you can start to quantify turbulence in general throughout the atmosphere on large scales, look at retrieving wind gusts from severe thunderstorms, and finally, if you have access to multiple Doppler radars with overlapping coverage, you can get the true wind vectors within the atmosphere in real time, where there are scatters present. And finally, with dual pole, it provides first and foremost classification. So we know what our scatters are. Are they bugs, are they large hail, or are they rain? It gives us a much better estimation of rain rate. It provides us with a volumetric indication of hail, so we actually have a map of where every pixel which is hail within it in 3D, using the full 3D volume. And there are more novel approaches coming out as the research progresses, such as looking at boundary layer height. Looking quickly at the 3D wind retrieval. So the plot here I have on the right is for the Cornell tornado event in 2015, where we had a tornado cross from a maritime supercell over the Cornell Peninsula. And you can see here we've got reflectivity plotted, but we've also got the X and Y, the U and V wind field plotted on top of that as well, which is not something you can get from a single Doppler radar. But when you have multiple Doppler radars, you can combine this information to resolve the equations which give you this three-dimensional wind field, including updraft and downdrafts as well. So this can be used to investigate, of course, circulations and updrafts associated with supercells and tornado development. The fine-scale structure of damaging downbursts, because we're resolving these features on the order of 250 meters, 500 meters resolution on the substorm scale. Looking at processes such as bushfire modified wind plumes and how these fire events are actually changing the local scale meteorology. Currently, this technique is possible, and we do run it for cases in Melbourne and Sydney, but it's currently not utilised operationally. So moving on to climatology applications now. You can see there's a bit of a map showing the global radar coverage as well. So there's a few key regions, of course the US, Western Europe itself has got excellent coverage. China's network is pretty much the second largest, or if not the largest in the world now. But Australia, we have quite a reasonable network for such a small population. So a project I'm involved in through the Bureau in Monash is developing open radar data set for the public from our national weather radar, network. So this data set is going to be hosted on NCI as a national data set collection. The aim here is to provide unrestricted research access to the entire archive and also provide a series of gridded products such as rainfall, hail size, azimuthal shear, which will be more easily accessible to the wider audience. An extensive amount of quality control has gone into this. We've done a lot of data archaeology, going through engineering logs, finding archives in weird places, pulling it all back together in a central unified archive. Also, a lot of calibration has been done, and a lot of this includes using satellite radar. So there are approximately 40 million radar volumes in this archive, and some sites have records going back over 20 years now, in particular for the capital city regions. And this will be the second largest public release of weather radar data, second only to the US NextRad network. So looking briefly at the satellite calibration. So we use the GPM and TRIM satellites to provide an absolute calibration over our radar sites. And we do this by volume matching. You can see the plot on the right there shows how we match the satellite pixel, which is shown with the larger boxes in the left plots are the elevation plane, the vertical planes, and the right plots are the horizontal planes. We match these large pixels from the satellite radars with the much finer pixels of the ground-based radars. And this allows us to compare common values to provide an absolute calibration. But of course, the devil is in the detail. There's obviously, these radars don't provide continuous coverage. We have to wait for passes, and often passes don't have any data points in them. So we may only get a dozen or more samples per year per radar for calibration. Satellite radars have a different sensitivity, a different band we have to take account for. And of course, you need a large number of samples to build up a robust statistic. We also use ground clutter for calibration as well. Normally, ground clutter is a real problem for radars because it obscures the data you actually want to be looking at. But it's relatively stable because the ground doesn't change, and we're always getting the same return from it. The map here shows the frequency of ground clutter at a very high reflectivity value around a radar up and down as a frequency of a percentage of the time. So we see there's a lot of pixels very close to the radar within the first 10 kilometers, which are present with a stable value almost 100% of the time. So we can track very fine scale changes in the radar calibration by using this information, which is normally just thrown out. So putting the satellite and the clutter together, we produce these maps. This map is for a Brisbane radar for the year 2012. The top plot is from the satellite calibration, and the bottom four plots are from the clutter calibration. You can see the satellite calibration is broken up into 5 periods, where the y-axis here shows us the difference between the ground-based radar and the satellite radar. So during these 5 periods, we have periods where it's running quite cold, the radar, compared to the satellite, and periods where it's had much better calibration. Given there's not too many samples for the satellite, defining where these periods start and end is a real issue. And we often have to go through engineering logs, and these logs typically aren't the best source of information, particularly the further back you go. So this is where the clutter steps in. We can see discrete changes shown here where we see increases in the value that the clutter is giving us, allowing us to pinpoint down to the very date where the changes have taken place. So these sorts of corrections for the radar data are absolutely critical, because even if we have, say if we have a reflectivity value of 50 dBz, which is typically associated with large hail, if that's off just by 3 or 4 dBz, which might just reduce the hail size by, typically that will be, with respect, maybe about a 10 to 15 millimeters change in hail size. But if it's miscalibrated, you're going to have your hail size coming from something which might be more like 50 millimeters down to something closer to 30 millimeters. So radars are very sensitive to calibration, particularly with retrievals. Once we've corrected the data sets, we can put together long-term climatologies. And I've got a couple examples here from Wollongong and Melbourne for a 10-year period between 2008 and 2017. So the first climatology set is mesocyclones. These relate to the traps of supercells across the domain. For the Wollongong radar, which is just south of Sydney, we can see there's a dominance of offshore supercells through that region, which actually matches up quite well with a lot of the cases we've had over the last 10 years. Compared with Melbourne, it's a little more mundane, where we have a few significant events, particularly the Christmas Day supercell of 2011, which show up quite nicely just north of Melbourne. The next set of plots are hail size and our rainfall retrievals. So for hail size, you can see over Sydney, we have a shift back inland again, because these hailstorms typically rely on the afternoon thermals which develop over a warmer continental environment. Melbourne itself, we see lots more events pop out, particularly from the northwest coming down, and these events are associated with storms which don't have this supercellular nature, but are still producing large hail. So this is a different mode of hailstorm we're picking up here. For rain rate again, we pick up a much broader series of events across both domains, particularly across the Sydney domain, where we've got a number of events in the southwest region, closer to the Great Dividing Range. One other problem when we're talking about retrievals of severe weather, say hail, wind, or flooding, the big problem here is verification, because active and passive remote sensing just cannot observe severe weather at the surface. It's always going to be some proxy. So another problem is in situ observations, such as weather stations, quite often don't even capture severe weather events as they pass through, because our storm cell might be too localized, for example. So as part of this work, we've also developed a new app to collect verification data back from the public. So this enables citizen science to report hail size, wind damage, flooding, and tornadoes. And we've called this app WeatherX for weather extremes. So this is going to provide verification for our retrievals, potentially even satellite retrievals as well, for understanding what the severe weather was at the surface. And you can get this app now through the Google Play and Apple stores. Moving on now to meteorology. So I'm going to touch on a few topics here. The first one is looking how radar can be used for bushfire monitoring. And this work was done by a PhD student at the University of Queensland, Nicholas McCarthy. So bushfire plumes. So bushfire plumes are quite a novel application for weather radar. We don't often think that if you point a weather radar out there, you're also going to measure fire. However, fires themselves, bushfires, do produce a very large amount of particles of all sorts of shapes and sizes, which are ideal to be observed by radar. However, bushfire plumes are typically much smaller than the convective clouds we're used to sampling. So usually they're under-resolved on radar. They'll just show up as a series of pixels here and there, but typically they're stationary and much easier to identify. However, if we can get in a lot closer and sample them much better by using technologies such as a mobile weather radar. So Nick used one of these mobile weather radars to explore the kinematics of bushfires, and this includes looking at the updrafts. So the change in updrafts support changes in the fire intensity through ventilation. Downdrafts, which are particularly dangerous on the firefighting front, where we have the fire direction changing rapidly. And of course, spotting, where we have the plumes lofting very large embers where we have the plumes lofting embers very large distances away from the fire and starting new fires. Just an example of one of the deployments at Mount Bolton in February 2016. We have the mobile radar set up there, with us in the orange. We have the conventional radar on the right. This is the Laverton radar in Melbourne. This is what it's seen of the event. So you've got a few thunderstorms around. The plumes in there, somewhere, but it's quite hard to define. It's sort of all mixed up with all the other features on the radar itself. We took our mobile radar out there and we were scanning this plume through a vertical cross section. So you can see the plume originates near where the origin of the radar here, at the left hand of the plot, and we can see the structure of the plume is captured beautifully. So we can see individual turbulence bubbles as part of that plume. On top of that, we also captured a lot of the precipitation around the fire as well. The radar that was used for this experiment was a dual pole radar, so it not only told us about the scatter and the wind, the radial wind from those scatters, it also gave us information about the shape. So the plot below here is a plot which relates to how homogeneous the particles were the radar was sampling. Within ash, you have particles ranging from fractions of millimeters up to very long stringy bark embers being lofted above. This gives a very low value for how coherent the signal is. When compared to rain on the right here, it has very large values. It stands out straight away. And this is because it has a very defined distribution of rain droplets. Just quickly looking at this data temporally as well. So we had this radar scanning about every 20 seconds for this case. There are three panels here. The top one is our traditional reflectivity, which relates to the intensity of the targets it's sampling. The one below that is related to the geometry. So the higher the value here, the more elongated the particles are in the horizontal sense. And the bottom plot relates to how coherent the signal is, so how homogeneous again it is, where we have the smoke having a very low value. We can see that using a radar at very close range, we can sample the fire structure with incredible detail, and we can also start to see larger particles falling out the fire relating to spot fires that are starting downwind of the plume itself. So using this sort of information can potentially be a critical step forward in understanding fire behaviour on the ground during a situation. Okay, moving on now to a project which was done at UQ by an honours student there called Jordan Brook. He developed a technique called HAILTRACK. So a big problem with forecasting hail is that the forecast relies on observing it very high up in the atmosphere, typically around 6 to 8 kilometres, and assuming it falls vertically down onto the surface, which never happens. Hail moves. There's a lot of wind in storms. It moves around the storm, and it also melts on its way down as well. So this creates a lot of problems for nowcasting hail, particularly at those really accurate fine scales, and particularly for high-end cases such as supercells. So the HAILTRACK technique combines physical modelling and multiple retrievals to overcome these issues. We take the full 3D volume of radar data and we detect the location and size of every pixel that has hail, and we size the value of hail out of that pixel using dual pole data. We then take the 3D wind retrieval of the environment and we say, if we have a hailstone here and it falls through the atmosphere, how is it going to move around within the storm itself? And finally, we combine a hail melting force speed model, so we can accurately simulate changes in size as the hail falls through the thunderstorm itself. We can see the plot on the right here. We can see the difference between the difference in size makes for advection. So we have smaller stones which are getting caught up, particularly in the low levels of the wind, the low level wind of the storm, and ending many kilometres away from where they started vertically. Large stones still advect, however. In this case, we have them advecting a couple kilometres, but in some cases they can advect up to 5 kilometres away from where they were detected. So we've seen this technique correct a lot of the displacement between hail observed aloft for high-end cases, and it really demonstrates the power of combining multiple retrievals for improving our physical understanding. Just a quick animation showing the traditional reflectivity horizontal cross-section on the left of one of these cases, and what HAILTRACK provides us on the right. So we have this HAILTRACK integrates continuously because we're using a time integration to take the hailstones and vect them down towards the surface. And this provides us with a much more continuous product of the hailstones as they land all on the ground. Even ahead of time, we can take these simulations and run them 10 minutes into the future and look at where hail will be impacting the ground then. All right, finally, I'm going to have a chat about a new project that I'm conducting as part of an international field campaign in Argentina next month. The Hail Pixel project is part of Reflectivity. So our understanding of hail that's used in weather radar retrievals and a lot of remote sensing comes from hail disdrometers. These are in situ instruments. We put them out just before a hailstorm, and they are impacted and measure the kinetic energy of hail. We have a couple examples on the left of the digital version up top, and a traditional hail pad down the bottom. So they have a sample area on the order of a square foot, and an accuracy on the order of about 1 centimetre. However, hail can be sparse, particularly for large storms, and these sorts of instrumentations become less and less effective when deployed in these environments. For example, the picture I put up here, if you put a disdrometer in any one of those spots for this storm, you quite likely miss the maximum hailstone size. And a lot of our understanding for developing these radar retrievals comes from this information. Finally, the solution is to take a new type of remote sensing. So if we take an off-the-shelf drone, such as a DJI Phantom, and fly that straight after a thunderstorm has passed, we can photograph the hail from above. We can sample very large areas at a very high accuracy. Thanks. So we've been testing this technique in Australia by printing 3D hailstones and putting them out across various different surface types. And we have trial captures from about 8 meters in altitude. And this can pick up these stones at an accuracy of around 3 to 5 millimeters. Using this technique, we can capture areas much larger than a square foot, on the order of 50 by 50 meters, within a time of about 3 minutes. And using automated size extraction from Python packages which provide machine vision libraries, we can extract many thousands of hailstones and build up a much more robust understanding of the hail size distribution, which will then feed into our improving retrievals from radar. Just in summary quickly, Australia's weather radar network is vast, and it's a truly unique data set for exploring sub-kilometre scales of precipitation across the country. There's many retrievals out there that people don't know about, so have a look at them if you have come across them in the literature. The archive length of radar data in Australia is considerable. We have over 20 years for a number of sites now, which is starting to become more useful for climate and will only become more useful with geopol. There are wide-ranging applications across severe weather, including bushfire monitoring and hailstorm nowcasting. And finally, we've got to continue integrating these new techniques, including satellite technology, aerial drones, for improving our understanding of retrievals. Thanks, some questions?